can be handy in future as well. So that's the first thing which I forgot, and definitely after today's class I'll do that. That was related to the ISOT test. Today we are going to discuss something about the tensile test. Okay, uh, this is one test. Though you haven't done it, from class 11 or even maybe even before, you know about the stress strain diagram, etc., etc., and that is basically a product of this particular tensile test. But tensile test is not only about the stress strain diagram. There are a lot of issues, at least for the mechanical engineers. Definitely, I must say there are a lot of issues related to tensile test, and probably all over the world there are hundreds of laboratories are there where people go for tensile test of different type of materials. As a mechanical engineer, we should not confine ourselves to the metals and alloys only. We can have mild steel, we can have structural steel, we can have aluminum alloys, we can have magnesium alloys, but we can have different type of composites as well. Alloy and composite are not the same thing. We can have different type of polymeric material, we can have different type of ceramic material, we can have glass, and all these components, frankly speaking, they come under the domain of mechanical engineering. It's not that as a mechanical engineer we are supposed to work on metals and alloys only. No, it's not true. At least in today's world, lot of components, lot of engineering components, they are being made of different other type of materials, different other than metals and alloys, different other type of materials. People are developing materials. And if you talk about research, I'm talking about practical engineering applications. If you talk about research, there is no limit. There is no limit. We can think about innumerable number of materials, and in some cases some in silico materials as well. That means some of the materials which in reality they do not exist, but in the computer we can create that sort of entities. So those sort of things we are not going to discuss right now, but we should accept that as far as the materials are concerned, different types of materials are concerned, tensile test is a fundamental test, or I should say one of the fundamental tests which we should focus on. So tensile test gives us a lot of information about the mechanical behavior of that particular material. Mechanical behavior. In some cases, we can try to correlate these mechanical behavior with some of the other behaviors as well. Not directly electrical, but in some cases, frankly speaking, let me share with you a small piece of work which I am involved in. We work a lot on a particular type of material which is known as a perovskite type of material. It's a special type of ceramics where the mechanical behavior has something to do with the electrical behavior as well. Not only that, another domain which I work is the domain of biomechanics, biomaterials, where we often find a particular component which every one of us, we carry within our body, that is the human bones. Those are piezoelectric materials. What does it mean? If I go for some mechanical stress, some electric potential develops. So some interconnections, sometimes, not always, some interconnections between the mechanical behavior and the electrical behavior can also be there. There are magnetostrictive materials. There are a lot of magnetostrictive materials where magnetic property can also be related to mechanical properties, yes, through the path of electromagnetism. So those are different things. I'm not entering into those things. This is not the class for that. In fact, you are not in that particular domain, in that particular level as well. In the postgraduate, in the PhD or something like that, definitely this sort of discussions can come in. It's not that you cannot understand, but still there are everything, they have their specified domains to be discussed. This tensile test, this particular graph, I know that most of you are quite familiar with. Some of you know that yes, there is an elastic part, there is a plastic part, this, that, you know. But right now, if you go through the video of the tensile test, I hope you will know about the details of the testing protocols, testing procedures. But why I have said, I have started with the word, with the sentence that yes, across the world people are working. Across the world, people are not only working on different materials, people are also working on the testing protocols. Testing protocol, what does it mean? That if I talk about testing of a piece of mild steel, and if I talk about testing of a piece of polymer, say high density polyethylene, you have seen the black colored water pipe, water containing pipe. Those are high density polyethylene pipes under the ground. Often we find those sort of pipes. For the municipal corporation, they install those sort of pipes, high density black colored pipes. So those pipes, that is also a mechanical component. They are supposed to carry some load. Water is flowing through that, so a lot of friction, lot of wear and tear, etc. takes place. So for them also, we should be we should know about their mechanical behavior. So stress strain behavior, tensile test of those materials, that is also important. Similarly, if I talk about, if you go to the Blue Earth workshop, you will find that a lot of turning operation, a lot of other operations, milling operation, cutting operation, a lot of things are going on. Those milling cutters, they have a particular material that can be high carbon steel, that can be silicon carbide, that can be silicon nitride. The stress strain diagram of those type of material, silicon carbide, silicon nitride, if you talk about different companies in India also, there are companies who manufacture ceramic based cutting tools because they are very hard. So that type of material, that also we can come across. So different types of materials are there, and for them the basic testing procedure, that is also not same. Let me give you a better example. Suppose I want to find out how much is the tensile strength, how much strength a human skin can withstand. Human skin can withstand. That is basically not a very three-dimensional sort of structure. It is more like a two-dimensional structure. It has length and breadth, but the thickness is very small in comparison with the length and breadth. If I take a piece, so in that type of situation, the particular protocol which we should follow in case of tensile testing is totally different from what we are going to follow in our laboratory right now, or maybe when we will come to the laboratory and we'll find a mild steel testing specimen. No, totally different. Protocols are different. There are large number of standards, protocols. We call them, say, ASTM protocol, American Society for Testing of Materials. We can go for DIN standards, basically German standards. We have Indian standard, IS specification. We have British standards. So different type of standards are there. Not necessarily all these standards exactly match. One standard testing procedure for mild steel done by ASTM and done by IS, Indian standard, may not exactly match, but more or less they match. More or less they match. But if I compare the testing protocol for a mild steel specimen with a polymeric specimen, with a biological specimen, with a specimen of human bone, with a specimen of human hair, with a specimen of human muscle, no, they do not match. They have different. So large number of even wood, even wood. You have gone for woodworking, and in the woodworking class, I do not know whether I was the class teacher or somebody else, but whoever it is, it it is clear that in case of wood, the strength of wood and the strength of mild steel, they are not same. So how to test the tensile test of wood, how to test the compressive stress test of wood, that protocol is also substantially different from that of mild steel. So that is the preliminary thing, that yes, standards and protocols are there. The question next comes, are we following a standard protocol? Yes, more or less we are following a standard protocol, and following that we are preparing the sample. What type of sample we are preparing? We are preparing a sample that looks like this. We call it a dog bone shape. Dog bone shape. The edges are more and this portion is smaller. The diameter in the mid portion is small, the diameter at the edges. These two portions go inside the grip. We are gripping it. These are basically grips. We are gripping them, and after gripping, we are pulling them apart. We are pulling them apart. So this sort of a structure is a dog bone shape. Yes, there is a curvature. You can see there is a curvature. There is a curvature. We cannot make as per my wish. No, I cannot make as per my wish. I cannot. I must follow a standard protocol. In our case, do we always follow that standard protocol? We are supposed to. We are supposed to, but that standard protocol, following that standard protocol, if I want to prepare the sample exactly following that, it may cost a lot of money. It may cost a lot of money. Exact chamfering, we call it chamfering. The exact the dimension of the radius of curvature of this filleting, the radius of curvature of the filleting in both the sides, they may not exactly match in our case. If I go for developing the material, developing the sample, manufacturing the sample in our own one workshop, that it may not be exactly matching, but we should appreciate, ideally speaking, we should always try to conform to a particular type of standard. It may be STM, it may be IS, it may be DIN, it may be British, whatever it is. We must try to conform to that. If it doesn't conform well, then you can expect erratic results. Erratic results. So our first take home message is, whenever we are going for a tensile test, this is applicable for the ISOT test also. Whenever we go for a tensile test, whenever we go for an ISOT test, whenever we go for a torsion test, whenever we go for some other mechanical testing like this, we should always at first conform to a particular type of standard. It may be ASTM, DIN, this, that, something. One. Second thing, during the experiment, I hope if you go through the video of the experiment, probably why this chamfering is done and other things are discussed there. If not, go through the video first. You will have to collect the video, or I told you in the last class, somebody should come to the university and I can hand it over. Otherwise, it's very difficult to say. You can try to collect it from some other section. If somebody has already got it, you can try to collect it from them. But if you go through the video, I hope it has been discussed there in the video that why this chamfering is done. If the chamfering is not done, if there is a sharp change in cross section, if the gradual change in cross section, this filleting is not done, if the curvature is not provided, then there can be stress concentration at that particular point. And when I will do this particular experiment, the whole material can break from that particular point because of high stress concentration. There are other issues as well. You will have to read a lot regarding this particular test. That's why I'm speaking a little bit in an elaborate manner. Not only that, these two edges, you can see these two edges, they are big edges. Big, the diameter is big. The whole thing is having a circular cross section. It's a cylinder, but at this edge, the cylinder has more diameter than the mid side, the mid domain. This mid domain, where the length, sorry, the cross section is same, all through same. This mid portion, this is known as the gauge length. Gauge length, GAUGE, gauge length. Okay. In some cases, I have heard people talking like gauge length. No, it's not gauge length, it's gauge length. So this is the gauge length where the cross section is uniform and small. These two portions, how much should be the ratio of the diameter here and here? The ratio of the diameter, bigger diameter and the smaller diameter, how much that should be? There is a specific rule to follow. We must stick to that rule. I will request you to go through, because you are exposed to internet, so you can find out in the internet what is the ASTM specification. Let me write it. ASTM specification of tensile test of mild steel. You can try to find out how actually the sample should look like. Just have a look. It's not that in our case we are exactly following that, but still you should know what is meant by a standard. Okay, that's all about the sample. Then what to do? What next? We will pull it apart. We will pull it apart, and we will pull it apart, keep on pulling it apart up to a point of rupture. Up to a point of rupture, unless and until it breaks. It's not obvious always that it will break from the midpoint. No, it's not always obvious. Some cases it can break from the midpoint. In some cases it will not. You are only in the second year. I am not going into the details of what type of fracture it will be, but I must mention one thing. The type of fracture when it breaks is known as cup and cone fracture. Cup and cone fracture. Let me draw it. The top portion is, after fracture, will look like this. The bottom portion will be like this. The bottom portion will be like this. So this is basically cup, and this is cone, and this is cup. Cone and cup. So we can call it cup and cone fracture. Why it is so? There will be scope for us maybe in the next 1 or 2 years to discuss about all these things. Okay, but here this much is clear, that we are going to expect a cup and cone fracture. For which type of material? The material we are using. What is that? That is mild steel. What type of material it is? It is ductile material. Yes. Now I should stop. I haven't discussed what is meant by ductile material. In case of ISOT test, I have given some hint. I have given some hint. Today, we will try to understand it clearly what is actually meant by, from engineering sense, what is actually meant by a ductile material, what is a brittle material. From the stress strain diagram, you remember the stress strain diagram maybe in class 11, 12, even in the maybe in the second semester, first year, second semester, you went through the coursework of strength of material. In the first chapter, I do not know whether you have gone through the first chapter. In some cases, I know people do not prefer to go to the first chapter, but that is the most vital chapter, I'm telling you. Most vital chapter, as long as the philosophy of the subject is concerned, and that philosophy we should not skip. We should not skip. We should never skip. We should go into the details of a stress strain diagram. And if a person, if a student, he understands the stress strain diagram and different minute intricacies, different minute variations of the stress strain diagram of different materials, and yes, the reason behind the variation clearly, I think at least 25% of mechanical engineering is done. A mechanical engineer, in the other way I should say, a mechanical engineer, he or she should be able to interpret the stress strain diagram like engineering drawing. A mechanical engineer, it should be able to, she should be able to interpret engineering drawing. Similarly, a stress strain diagram, a mechanical engineer, more correctly, a metallurgical engineer, they should always be able to interpret the stress strain diagram. What does it mean? What type of information we are getting if we just look at the stress strain diagram? We can have a stress strain diagram like this, but that does not mean for all materials the stress strain diagram will be like this. So if I draw a different type of stress strain diagram like this, suppose this is a stress strain diagram. This is a stress strain diagram. This one and this one, totally different. This is a stress strain diagram. This one, totally different. A mechanical engineer, he should be able, she should be able to interpret what does it mean. What are the type of information I can get from this, or there can be plenty of other. I am just yesterday I was teaching in one class in postgraduate. The stress strain diagram was something like this, going like this, almost horizontal, and then going up steep. That is a typical type of stress strain diagram of a particular type of biological tissue. Biological tissue, yes. As a mechanical engineer, we should be able to understand what does it mean. So, lot of variations of stress strain diagrams are there. So far, whatever I have discussed, let me just tell you, summarize. One, we should know about the standards. Standard means what are the standard practices of testing? What are the standard dimensions of that particular specimen which we should use for a particular type of test? For a mild steel, we are using this type of specimen. No, this type of specimen is not used in case of a biological testing. A biological, for a skin, no, we are not going to use it. For a particular type of glass, we may not use it. For a particular type of wood, we may not use it. So the type of specimen is not universal. The type of specimen is not universal. The type of specimen differs, varies from material to material. That is one thing. Second, the stress strain diagram which we will get after the tensile test done. After doing the tensile test, the test stress strain diagram which we get, the stress strain diagram, what it can offer, what type of information it can offer to us. Endless, endless information, stupendous amount of information it can offer us. Okay, whether we are in a position to understand that or not, that is also a big deal. So that is the preliminary thing which we should discuss primarily about the tensile test. Now let us come to the point. What we are going to do now? We are going to know. Not here. I am not in the laboratory. I am sitting back home. Today I will go to the university for some other purpose. In the laboratory also I will go for a different thing. But anyway, we are not going to do the tensile test right now. But we are basically guessing without doing the test. If you follow the video, you will see the test being done. But without doing the video, without going to the video, let me tell you some fundamental things. Two fundamental things I have already mentioned: variation in test protocol and variation in the stress strain diagram. But now let us enter into the minute intricacies of this particular test. If you have any query, please ask. I used to know a person who was always bubbling with questions. Aranno Subro. Yes, he is here. Do you have any question, Aranno?
স্যার অন্যান্য যে মেটেরিয়াল গুলো হয় সেক্ষেত্রে স্যার ওই টেস্ট স্পেসিমেনের স্ট্রাকচার গুলো কিরকম হয় স্যার? লাইক ধরুন বোন যেটা বলছিলেন আপনি স্যার, বোনের ক্ষেত্রে মানে কিরকম
আচ্ছা, ঠিক আছে,
টেস্ট?
ঠিক আছে, আমি একটু পরে পরে ডিসকাস করবো, ঠিক আছে? ডিসকাস করবো, সবটা হয়তো এখানে ডিসকাস করা যাবে না, বাট আমি তোমাকে জাস্ট একটা আইডিয়া বলছি যে ডিফারেন্ট টাইপ অফ গ্রিপস আর অ্যাভেলেবল, ঠিক আছে? আমরা এখানে যে গ্রিপটা ব্যবহার করছি, দ্য টাইপ অফ গ্রিপ উইচ উই আর ইউজিং হিয়ার, দ্যাট গ্রিপ, তুমি স্যাম্পলটাকে আমি বললাম, ইটস বেসিক্যালি আ সিলিন্ড্রিক্যাল ক্রস সেকশন স্যাম্পল। এইরকম একটা স্যাম্পল উই আর using the cross section is cylindrical. So grip টাও হচ্ছে cylindrical hole, we have a cylindrical hole on top, we have a cylindrical hole, I mean a circular hole on top, circular hole on bottom. In case of a specimen like bone, in case of a specimen like say skin, in case of a specimen like a fiber, okay, say fiber reinforced plastic, we do not go for this type of specimen at all. There we go for the cross section is rectangular. It's a plate type of structure. It's a plate type of structure. Okay, so there are other things as well. In some cases, even the plate type of structure is not possible. Suppose for a single fiber to be tested, we often go for single fiber. In our university also, we have some machineries through which we can develop some this sort of single fibers. So that's that type of single fibers. It's not possible to develop this type of structure. The dimension, the thickness of the single fiber itself is few micron. How can you do this sort of thing? So that sort of setups are also possible. So it's not only the question of the dimensions and other things of the specimen, the grips, the type of grips, type of holding the specimen, that also varies a lot. Different type of grips are there, and I'm just telling you, two big companies who manufacture this type of instruments for tensile test. One is MTS, one is Instron. One such grip, it cost nearly few lakhs, maybe 5 lakhs just for one grip. Okay, so you can understand what type of precision things are there inside. Okay, so it's not only a question of specimens, the grips are also depending on the specimen. There are n number of different types of grips. Okay, let us come to the point. If we focus on the stress strain diagram, I'm not entering into the details of the experiment. That will be done during the video. You go for the video, and the teacher concerned, he will be explaining that particular video, what is going on during the test. I'm not entering into that. I'm entering into something else, some minute intricacies. Okay, from the experiment, you will basically get not the stress strain diagram, you will get the load deformation diagram. You will get the load deformation diagram. Now we are basically dividing the load which we are applying with the original cross section, because you know why I'm using the term original, because with time, as I am keeping on the load, I'm putting on the load on the sample, then definitely its cross section will also reduce, and after a certain point, that cross section will keep on reducing substantially. Substantial reduction of the cross section takes place. But when I am finding out the stress sigma, usually we denote with sigma, which is L by A. That A is the original cross section, the initial cross section. So we are finding out sigma by dividing the instantaneous values of load. Each and every point, whatever value of load I am giving, divided by the original cross section, not the instantaneous cross section, to find out sigma. That sigma, we call it engineering stress. Engineering stress, not the actual stress. Why engineering stress? Why not actual stress? Actual stress is basically instantaneous values of L divided by instantaneous values of A. No, we are not going for that. It is very, very difficult to find out the instantaneous value of A at each and every moment. It's not so easy. It's not so easy. What we do in lieu of that, we go for engineering stress, which is L, instantaneous values of load, divided by the original cross section, engineering stress. What about the other stress? L divided by actual A, we call it true stress. We call it true stress. It's surprising that the opposite of engineering is true. Usually what you have learned so far, opposite of true is false. So engineering is synonymous with false. You have time still. If you like, you can change your stream and go to somewhere else. But it's obvious that engineering is opposite to true. Okay, actually, we should say in the other way around. We should try to put our claim in the other way around, that yes, engineering stress is L divided by original A. That's true, but that is the practical stress, and this is the ideal stress. We do not care about this hypothetical or ideal thing. We depend on the practical thing. That's why we focus on engineering stress. This is not the false stress, rather it is the practical stress, and this is the hypothetical stress, or this is an ideal stress. We do not care about the ideal things. Nothing in the world is ideal. Everything in the world, we the engineers deal with, they are practical things. We are practical people, we deal with practical things, and this is the practical stress. Fine, we can discuss a lot about this thing, forget about it. This is engineering stress. Instantaneous load divided by the original cross section. I have told you that there is a real difficulty in finding out the instantaneous values of cross section at each and every moment. It's difficult. To make it simple, we have gone for this. What about strain? This is deformation. Deformation, in case of pulling something apart, I am pulling this pane apart, I am pulling this pane apart, so definitely the change in length will take place, and that change in length will not take place in a one small domain. Along its length, only on the top portion will change in length. No, the whole thing will change its length. The change in length we can measure the change in length, the instantaneous change in length, that is basically deformation. That we can note it down from the experiment. We can note it down very easily. We can note it down how much is the deformation. We can use an LVDT, we can use a strain gauge, etc., etc. For strain gauge, we can directly get the value of strain. I'm not coming to that, but we can use an LVDT, we can use some other technique to find out that how much is the displacement between the two grips. How much is the displacement between two grips? If I know the displacement between the two grips, that is basically the elongation. Okay, fine. Now that elongation divided by the original gauge length will give in the experiment. Definitely, I think the teacher concerned, he has explained all these things. So L by D, we can convert this into stress by strain. This deformation divided by original length, we can get strain. So we can convert this load versus deformation curve, which directly we are getting from the machine, from the plot. The machine has a plotter. From the plot, what we get, load versus deformation. We can convert it to engineering stress strain diagram, no problem. Now let us come back to that engineering stress strain diagram. I am basically just giving you one sort of it's sort of a disclaimer that from the experiment you are not going to get the stress strain. From the experiment you are going to get the load versus deformation. Now from that we are getting engineering stress, engineering strain diagram. Now the material which you are going to deal with, that particular teacher, whoever it is, he will deal with, I know, with mild steel, because that is what we do. In case of mild steel, we'll get that the stress strain diagram is something like this. Something like this. What does it mean? There is a linear part with a slope. There is an upper point. There is a lower point. There is a curve. There is a highest point of the whole graph. Highest point. Then it drops to some extent, and at this point the sample breaks. Actually, what we should try to understand, this is basically increase in the stress. Yes, increase in the strain as well. Up to this point, everyone knows, you remember it very well, that this is basically the elastic domain. Up to the elastic point. What is elastic point? The point or the stress up to which we can go, and if up to which stress we can go, and if I release the stress, if I release the load, it will come back to its original configuration. So that is the elastic point. After this particular point, the plastic domain starts. But we should keep in mind that this portion is linear. So can I say that the elastic portion is linear? Yes, apparently it's so. But in some of the materials, it may be so that we have a linear elastic part. What is elasticity? I have already mentioned. If I release the load, it will come back. And there can be a non-linear elastic part as well. That means the linear elastic part is followed by a non-linear elastic part as well. Is it always true that the linear elastic part is followed by non-linear? Can there be the opposite also? The non-linear elastic part is beginning from the start? Yes, it can be. In case of polymers, often we find it, the non-linear elastic part, not the linear, non-linear elastic part. If I release, it will trace back. It will trace back. Okay. So elasticity has nothing to do with only linearity. But in case of metals and alloys, we can jolly well accept that the linear part is basically the elastic, no problem. But ideally speaking, for all materials, it may not be uniformly true. There can be a a non-linear elastic part as well. Maybe in between, maybe after this, maybe before this, etc. Okay, from the beginning it's non-linear, it can be, but still elastic. After this linear part, there is a non-linear part that can be. So everything is possible, but for mild steel, no. For normal metals and alloys, usually practiced metals and alloys, no. So this is the stress strain diagram we usually encounter. We usually encounter for metals and alloys. No, not for all. Not for all. Now what we see, there is what you are saying. We were saying that after this we have a plastic domain, elastic domain in this side, plastic domain. This is plastic domain, this is elastic domain. Now the question is, what is meant by plastic domain? The stress beyond which, if I load it and then unload, it will not come back to its original configuration. That particular point is known as yield point. Yield point. Now the question comes, are the yield point and the elastic limit or the proportional limit, are they necessarily the same point? Not always. But in case of mild steel, in case of majority of metals and alloys, they are necessarily the same point. Which 2 points I am talking about? Rather 3 points. One is the proportional limit, up to which stress is directly proportional to strain. Elastic limit, up to which elasticity prevails and it is linear in nature, beyond which the material deforms or starts to deform in a plastic manner. That means if I release the load, it will not come back to its original configuration. For mild steel, for aluminium, for different type of metals and alloys, for majority of them, not for all, for majority of them, these 3 points are almost, they coincident. They are basically at the same point. But if you say so, you may find few people asking or giving you zero, because there are two different yield points in case of a mild steel. This is a special type of steel. Why does it happen? Do we expect this sort of thing in case of a low carbon steel? Do we expect this sort of thing in case of a high carbon steel? Do we expect this sort of thing in case of aluminium or aluminium alloy or brass or some other metals? No. No. Why for mild steel? Why for mild steel this particular thing happens? I think towards the end of this particular coursework, we will get chance. We will try to discuss that. Right now, let us accept that in case of mild steel, actually from engineering point of view, we consider the yield point not here, rather here. We call it higher yield point, HYP. We call it lower yield point, low LYP. This lower yield point, usually we consider the lower yield point to be the yield point of mild steel. But we should keep in mind that once we cross this particular stress, say sigma 1, once we cross this particular stress, the plastic deformation starts. The plastic deformation starts, but still we accept this because there is a particular region starting from this region. There is a particular region which resembles the similar type of region for other materials. Let me draw another graph, then it will be clear. For aluminium, the graph is something like this, or maybe little bit like this. Here you see it's not dropping like this. Here it's not dropping. So that particular drop is a special type of phenomena observed in case of mild steel. For other materials, for generally speaking materials, we can draw the stress strain diagram like this. Straight portion, a small curvature, and then going up, and then again going down like this. So this sort of a diagram is for metals and alloys. For mild steel, it goes down a bit and then it goes up. This portion starting from the lower yield point, to the highest point. We call it UTS, ultimate tensile stress. Up to this point, this domain, this region is known as plastic flow curve. Plastic flow curve. Take it from me, believe it, that for different materials, the plastic flow curve is something unique. For different materials, they have their own plastic flow curve. If you vary the carbon percentage a little bit, in case of steel, carbon percentage we can vary. We can go for cast iron, we can go for low carbon steel, high carbon steel, mild steel, lot of varieties we can go for them. If we vary the carbon percentage, if we vary the composition, if we vary the heat treatment mechanism, etc., the plastic flow curve will be different. So plastic flow curve is something. Plastic flow curve is something which is basically a signature thing, a signature characteristic for any material. Keep it in mind. We often talk about that this domain is known as the strain hardening domain. Strain hardening domain. The experiment, when some people will discuss about the experiment, probably he will use this particular term, strain hardening domain. That's okay, that's good. Why we call it strain hardening domain? Again, please keep these things for the last class. At the last, if you are interested, I can go for some discussion in the light of material science. In the light of material science, then we will try to understand why this drop in case of mild steel, why this particular domain is known as the strain hardening domain. We call it plastic flow curve, that's fine. Plastic flow curve, but why strain hardening domain? It's a big term. Plastic flow, okay, fine. The material starts to deform in a plastic manner. We call it plastic flow or plastic deformation curve. That is that I can understand. But why strain hardening? What is the meaning of strain hardening? I think we'll have to wait a bit. In the demonstration, if somebody explains, that's fine. That's fine. But I personally do not feel that it is high time for us to learn about what is meant actually by strain hardening. Let us wait a bit. Let us wait a bit, maybe a couple of months or maybe a month or so. We'll discuss about this thing. Let you move a little bit ahead with the material science coursework, or maybe if it is already done, I will refer back. I'll refer back. But once all the experiments and other things are done, I'll go back to this discussion. Now there is a plastic flow curve, and this is UTS, the maximum stress. Okay, what is meant by maximum stress? This stress is engineering stress. This is the maximum stress. That means it corresponds to the maximum load. Maximum load it can withstand. So load is here. Now what happens? It is going down. It is going down. Down means the stress is going down. This is engineering stress. The stress is going down. If the stress is going down, apparently what we believe, that the load is going down, because we are dividing the load with A, and the A is constant. So if the stress goes down, that means the A remaining constant, load is going down. But actually, frankly speaking, if I plot the true stress strain diagram, it would have been like this. It would have been like this. That means load is still going up. But because the cross section after this point substantially gets reduced, but we are not taking care of that particular reduction. That's why this is going down. It's showing to be going down. Actually, load doesn't go down after this. Actually, cross section goes down. So even if there is small increase in load, the high reduction in A causes it going down and down and down. Okay, so actually the load after this point, it still increases. But the cross section goes down. But we are dividing with the original cross section, so the load is not increasing too much, but the cross section is going down to a great extent. So it's going down like this. It's going down like this. Load is not increasing too much. That's true. Not increasing too much. Load is also going down to a bit, but whatever is the fluctuation in the load, that we are not taking care in this particular domain. This particular domain is known as the necking domain. Usually this was the specimen, not exactly, but the mid portion is like that. But now the specimen has started to form a neck like this. A neck like this. A neck formation starts. A reduction in cross section starts. But Once we cross UTS, there is another thing which I am not sure whether it will be discussed during the demonstration. That is known as Loider's band. Loider's band, Leuder, Loider's. Loider's band. What is Loider's band? You have gone through the coursework of material science. There is a particular term I will request you to revisit, that is CRSS. What is that? Critically resolved shear stress. Critically resolved shear stress, CRSS in short. What happens when we keep on putting the load at any moment? At any moment, once I cross the yield point, the defects inside the material, defects means the dislocations, the line dislocations and screw dislocations, they start to move. They start to move. And that is basically responsible for causing the plastic deformation. Fine. What happens? After crossing UTS, that particular dislocations, huge number of dislocations, maybe millions, they form a roughly 45 degree, why 45 degree, etc. We'll discuss later. They form a 45-degree sort of a plane with the axis. With the axis, they make a 45-degree plane and they are coming to the surface. From inside the material, suppose you are standing inside the material, with the dislocation, you will start to move in a particular direction, in a specified direction because of certain reason, and you will reach the surface. How can we understand that Loider's bands are formed? If we put a traveling microscope here, we will find, not here, on the whole surface, because we do not know where the Loider's band will actually form. We will find initially the metallic sample. Yes, you are using a metallic sample. They are used to have a metallic luster. Chok chok ekta bhab thakbe, it should be a metallic luster. That metallic luster will not be there in that particular, along that particular region, which is 45, which is making a 45-degree angle with the axis. That particular band, we call it slip band, or in other words, Loider's band. Loider's band. In case of material science, you have heard about slip planes. You have heard about slip system. This is nothing but that slip. The dislocations, they start to move and they form the Loider's band. So the Loider's band is nothing but, it denotes excessive plastic deformation had start to take place. Excessive plastic deformation. Up to UTS, yes, plastic deformation is definitely there, but within a control, within more or less up to a particular value. But after that, excessive plastic deformation starts to take place. What does it mean? It is basically causing some change in the cross section. Once this Loider's band starts to form, the immediate effect is formation of this sort of things. This sort of things, this sort of necking. And finally, this neck, it doesn't come to a point. This neck, you see the cross section is coming down. Here the cross section was more, here the cross section is less. Finally, when it breaks, it doesn't come down to a point. No, it doesn't come down to a point. But it breaks, forming a cup and cone fracture, which I showed. We can discuss a lot why it's not coming down to a point, why it is basically forming a cup and cone fracture. No, not now. Not now. If it is discussed during demonstration, that's okay. That's not up to my choice. I don't like all those things to be discussed right now. We lead to finally a cup and cone fracture, but that is not all. Finally, fracture takes place here. If I once again draw the stress strain diagram, and now I'll conclude. I'll conclude with some small messages. Small, but I personally feel those are important messages. But yes, after this also I'll have to draw one more figure. What are the informations we are getting? Yes, during demonstration, the teacher concerned will tell you what are the information. I'm just showing you one more thing, which I promised. What is that? This is, say, yield point. You can call it proportional limit, etc., etc. Higher yield point, lower yield point, plastic flow curve, UTS, fracture point. Let me drop a perpendicular. Let me drop a perpendicular. If this is stress, if this is strain, what is the unit of this particular thing? This particular area, what does it denote? This is Newton per millimeter square, right? What about strain?
Sir, এটা তো unitless.
Unitless. That means millimeter per millimeter. Can I write it like this?
Yes, sir.
That means Newton millimeter per millimeter cube, the area.
Yes.
Newton millimeter means energy.
Yes, sir. মানে এনার্জি পার
Millimeter
ইউনিট
cube,
ভলিউম।
millimeter cube volume. So energy per
পার ইউনিট
unit
ভলিউম।
volume. So the area denotes energy absorbed up to the point of fracture by the material per unit volume. Okay. Now, if this is the stress strain diagram of mild steel, and on that particular stress strain diagram, using the same frame, if I draw the stress strain diagram of glass or maybe silicon carbide, it will be something like this. You see the area under the curve. So the area under the curve here is much smaller. So it absorbs, glass absorbs silicon carbide, silicon nitride, and that type of ceramic materials. Even high carbon steel or cast iron, not exactly same. But the stress strain diagram, it doesn't have this much of area under the curve in case of high carbon steel. In case of cast iron, it's not like the mild steel. So in mild steel, huge area under the curve. In case of glass, small area under the curve. This material is having is capable of withstanding high amount of energy before fracture. This material is capable of withstanding low amount of energy before fracture per unit volume, both per unit volume. That means this material, that means mild steel, it is capable of withstanding more energy prior to fracture. We can call it, like the previous experiment which we did, ISOT test, aluminium was more capable to withstand high amount of energy. We called aluminium to have higher toughness than brass because brass used to fail cheaply without absorbing high amount of energy. Brass used to fail. Even today, if I do the experiment, it will fail cheaply. So it will not absorb much energy during impact testing. That was impact testing. Even though I am not going for impact testing here, we are basically doing a quasi-static experiment. What is meant by quasi-static, etc., will be described, I hope, by the teacher concerned while doing the experiment. What is meant by quasi-static? But this is not an impact testing. I'm not using a hammer to give a blow. No, not at all. But in that case, we found out one material absorbs more energy, one material absorbs less energy for fracture. Here also I am going to the point of fracture, and I am finding one material absorbing more energy, one material absorbing less energy. So once again, I have selected this particular experiment as because it has some connectivity with the previous experiment. In both the cases, what we are going to conclude? We are going to conclude, yes, we can have some materials which can withstand high amount of energy, be it in impact. I am not telling the same material under impact how it will behave. No. But at least we can see that in quasi-static testing also, in tensile testing also, we are finding some material which are absorbing more energy and some material which are not absorbing that much of energy. Okay, fine. We can again call this material as a tougher material than this one. What is toughness? We know the amount of energy absorbed or resistance to fracture, resistance to crack propagation. We discussed in the last class. So this particular material, mild steel, will offer higher amount of resistance to fracture. The same type of specimen, no, it's not offering that much of resistance to fracture, that much of energy is not absorbing. So this one is tougher, this one is less tough. Yes, still I'm not deliberately using, I'm not using the term ductile or brittle. Now I'll go for that with one more small thing. What are the different informations we can get, etc.? I have just touched upon one, energy absorption. What about the other? How to define UTS, how to define fracture stress, how to define yield point? More or less we have discussed. The teacher concerned, he will also be discussing. I'm sure about that. Now let me draw once more. First, the stress strain diagram of the mild steel which we are doing. What is there on this axis? Strain. What is there on the x-axis? Stress. Now, if I drop a perpendicular here, this particular distance, can I say that this is basically the elastic strain? I hope I can. Elastic strain, usually how much it is? 0.2%. What does it mean? If the length of the specimen is 100, I am going to 100.2, and then I am entering into the plastic domain. So up to 100.2, that change in length, that is elastic change in length. If I cross and I becomes 100.3, 100.4, 100.5 or 101, no, I am in the plastic domain. I'll not be able to come back to the original configuration anymore. Okay, so 100.2, roughly from engineering practice, we consider 0.2% strain as the elastic strain of engineering materials, majority of the engineering materials, metals and alloys. What about the plastic strain? If I drop a perpendicular, yes, it is breaking there. So this much is the total strain which the material can absorb or the material can sustain before fracture. How much it is usually? For mild steel, you will find it to be, I do not know how much result you got during the experiment, but it is supposed to be more or less around 20-25%. 20-25%. That means if the original length was 100, after crossing 120 or 125, it is breaking, or maybe even 130, depending on the material composition, etc. It can be a little bit more. So 20-30%, something like that. If, keep it in mind, that's universally true. If a material fractures after absorbing, after sustaining more than 5% elongation, we call it a ductile material. If it fails before 5% elongation, we call it a brittle material. We are basically using a thumb rule. This is nothing but a thumb rule. Thumb rule. If the material, suppose I am starting with 100 millimeter, I am going to 104, it is breaking. We will call it a brittle solid. If it is breaking at 106, 107, 110, 120, 30, 50 or even more, we'll call it a ductile material. Yes, I know. It can only be a thumb rule. We should rather focus, if somebody asks what is ductile material, yes, I can use this definition. I can use this definition. No one can contest. This is universally accepted for the practical engineers. For the engineers, I should not say practical engineers. Engineers are always practical people. For the engineers, for the practicing engineers. But we should always keep in mind that 104 and 106, not too much different. Not too much different. One material failing at 104, one material failing at 106. Is there a big difference? No. So we should also keep in mind that though we are using a thumb rule of 5% elongation, 5% elongation as the cutoff. If it is more than 5%, it is ductile. Less than 5%, brittle. But still, it should be kept in our mind that yes, if it is 104 and 106, it's not very wise to call them ductile and brittle. Rather, we should say one is more tough than the other. One is slightly more tough than the other. That's all. That's all. Is it clear? I'll go to another point. Is it clear?
Yes, sir, clear, sir.
Fine. Now let us go to, if I compare the stress strain diagram of this thing with that of, already I have drawn that particular silicon carbide, silicon nitride. Yes, for brittle solids, the stress strain diagram is like this. The slope is little bit steeper. The slope, what does it denote? It's Young's modulus. Stress by strain, Young's modulus. Slope is little bit deeper, but the area under the curve is smaller. Yield point is higher. To be noted, here is the yield point for the high carbon steel. Here is the yield point, or for the ceramic type of material, for the silicon carbide, silicon nitride, here is the yield point. What about the polymer? In case of the polymer, the stress strain diagram is something like this. Something like this. It can go on increasing, and when it breaks, maybe if I drop a perpendicular, I will find the strain to be 200%. Not 30%, not 40%, not 20%, maybe 200% strain it is withstanding before fracture. So we can have different type of materials. Right now, I think this is good enough. But one more point I should add. Right now, this is good enough to compare how a brittle solid looks, how a ductile solid looks, and how a polymer type of material, which is, you can call them superplastic sort of thing, highly deformable material, they can show like this. There are certain type of material, we call them super elastic material. Okay, in the last class, I will touch upon those things. There are some special cases. But now I will request you to do one thing. Just maybe 2 minutes left. I'll have to stop because I'll have to go to the university as well. Uh, One more thing. What is that? This particular part, linear part, I'm talking about mild steel, not about the other materials. I'm talking about mild steel, a standard material, mostly used, abundantly used material. Okay, it is easy to deform. Why it is abundantly used? What is the composition of mild steel? What is the percentage of carbon? You should check. As an engineer, you must be careful about that. What is that this particular linear zone? We know this is elastic zone. Very good. Now this elastic zone, we always know in the grand viva after 4 years, I will ask, what is Hooke's law? Hooke's law is not between stress and strain. It's not between stress and strain. Hooke's law originally was between deformation and load and deformation. Up to elastic point, up to a certain point, up to the elastic limit, load is directly proportional to deformation. That was originally the Hooke's law. Then from that people derived, yes, we can go for the stress is proportional to strain up to elastic limit. But original Hooke's law is not between stress and strain. It was between load and deformation. Fine. That's not a big deal. That's not a big discovery as well. What I would like to request you, you told me in the last class that you have followed the book of Timoshenko and maybe Björn Johnston. I would request you, uh, you can try to find out our book as well. No, no. Once again, I am telling you, not advertising for my book.
স্যার
Our
এর ডিপার্টমেন্টে পাওয়া যাবে স্যার?
department deposit. Yes, even
ওকে
if you do not go for our book, you can write what I am writing here in the net and get a clear cut idea about that. This is Romberg, Romberg, Romberg Osgood, Romberg Osgood. Okay, Romberg, Romberg Osgood relationship. Try to write it in the internet, in the maybe Google or some search engine, and try to find out what is Romberg Osgood relationship. I am telling you, it is always our tendency. It's a human tendency, human nature. P is equal to mf is basically a formula. It's not that initially before Newton came, the objects, they did not follow P is equal to mf. Objects always followed P is equal to mf. Newton tried to find out, yes, what is the relationship, and he found it out to be, proposed it to be P is equal to mf, and later on it was verified. That's fine. Here also, we are getting the stress strain diagram. Doing the experiment, we are getting the stress strain diagram. Up to this point, it is obeying Hooke's law. Up to yield point, up to elastic point, I should not say yield point, up to elastic point, proportional limit, it's following the Hooke's law. Fine. Romberg-Osgood relationship is that relationship, that mathematical relationship, which correlates stress and strain up to the point of fracture for an engineering metal or alloy. For an engineering metal and alloy, Romberg-Osgood relationship is that typical mathematical relationship, a small relationship. All the big formulas which change the whole world, like E is equal to mc square, P is equal to mf, are small equations. This is also a small equation, not a very big one. Not that much small, but this is also an equation. It did not change the world, but it offered a lot of benefits to us in future. If somebody goes for research, he will understand. That particular Romberg-Osgood relationship, try to find out, locate it from internet, and try to understand why that Romberg-Osgood relationship can be of some use to us. Can be of some use to us. Okay, so the whole curve, not only the linear part. The Romberg-Osgood relationship, it has a linear part. It is a two terms are there. Two terms are there. Strain. I want to find out strain. It is a function of stress. Function of stress, but first part it's a linear function of stress, and second part is a non-linear function of stress. So that particular combined equation in at one part of your notebook, you can just note it down. What is Romberg-Osgood relationship? That is the relation between stress and strain for normal engineering metals and alloys. We should also take a note of it. Okay, this much I can say. Another small point I should note. What is that? I'm talking about different type of materials, metals and alloys, ceramics, these, that, etc. Let us focus on the metals and alloys which are mostly used, abundantly used in mechanical engineering. Even the design classes, you will find in majority of the cases, we will focus on metals and alloys. That's reasonable, no doubt about that. The question is, all these metals and alloys, they are not going to be used at room temperature. We can use it for cryogenic engine. We can use it for high temperature application. Lot of things can happen. Now, depending on the temperature, how the stress strain diagram will change, that is also a big issue. That is also a big issue. I am telling you, if we increase the temperature, in the last class we discussed that the material becomes more and more tough. That means that is also reflected here. If I increase the temperature, the material will show bigger area under the curve. Bigger area under the curve. But one thing is for certain, that if this is the slope of the stress strain diagram, at room temperature, the slope will go down and the yield point will come down. Yield point will come down. If you go to the smithy shop, yes, in the smithy shop, basically that particular worker in the smithy shop, he is basically increasing the temperature and the yield point is coming down. That means he will not be able to, he will not have to use high amount of load. He can work at a low amount of load and cause deformation. Yes, he wants to deform, he wants to give it a shape. So if I increase the temperature, the stress strain diagram also changes. If I increase the temperature, the slope goes down. If I decrease the temperature, the slope goes up. That is one thing. And second issue, I will just leave it to you. I will not discuss a single word on that. What about the strain rate? Strain rate. I have mentioned that we are doing the experiment, the tensile test, as a quasi-static experiment. I'm pulling it very slowly, very slowly. You try to find it out what is meant by quasi-static. If it is discussed in the demonstration, that's fine. Otherwise, you try to find it yourself. What is quasi-static and what is actually the rate of loading, the rate of strain, rate of strain. How much is the rate of strain? I'm pulling apart, but at which speed? Am I pulling it very fast or am I pulling it slowly? This sort of thing is very important. Is there any effect of strain rate on the stress strain diagram? Is there any effect of strain rate, loading rate on the yield point? I'm just keeping it for you. You just try to find out, maybe from internet, maybe from books. In the next class, we'll discuss.
মানে স্যার এখানটা ওই কোয়াসিস্ট্যাটিক বলতে মানে যতটুকু জানতাম স্যার মানে যদি কোনো একটা মানে পাওয়ার সিরিজ হিসেবে যদি আর কি জিনিসটা এগোয় তাহলে সেটাকে মানে কোয়াসিস্ট্যাটিক বলা যেতে পারে। লাইক স্যার আমরা মানে
I am asking you from practical point of view. Quasi-static, the term usually means that we are pulling it apart at a speed in such a way so that at each and every moment we can consider instantaneously, at each and every instant we can consider it to be as if it is static, as if it is static. The effect of strain is so small, so small, that we can assume that each and every moment we are going a static experiment. It is almost static. That's why we call it quasi-static. There is a particular limit known as 0.5 millimeter per minute. The strain rate is 0.5 millimeter per minute. If I go more than that, it is no more quasi-static. It is becoming a dynamic experiment. If I go even higher, it is becoming dynamic and dynamic and dynamic. Dynamic test result and static test result or quasi-static test result, they are not same. There is some difference. I ask you to try to find out how much is the difference. ঠিক আছে, একটু খুঁজে দেখো।
ওকে স্যার।
Okay, how many people are there? Can somebody read it out? 17.
16 আপনাকে ইনক্লুডেড
Okay, আমাকে নিয়ে 17. Okay, I am also a student, no problem. Okay, few people are missing the class. Please ask them, don't miss this particular laboratory class. At the end, he will have to pay for this. Okay, please ask them. Anyway,
স্যার আপনি যে ভিডিওগুলোর বললেন কটা ভিডিও, তিনটা কি মানে
ভিডিও থাকবে তোমাদের বোধহয় 5টা বা 6টা এক্সপেরিমেন্ট আছে, সুতরাং
না, আমি
প্রত্যেকটা
একজনকে
আলাদা করে।
জিজ্ঞেস করলাম, ও বললো মানে ফার্স্ট এক্সপেরিমেন্টের ভিডিওটা ওর কাছে আছে আর কি, মানে ওদের সেকশনে।
ও আচ্ছা আচ্ছা আচ্ছা, হ্যাঁ ওই মানে তুমি যদি স্প্লিট করে করে ধরো, নাম্বার অফ এক্সপেরিমেন্ট হচ্ছে ধরো 5 or 6, নাম্বার অফ ভিডিওস ক্যান বি মোর, কারণ একসাথে সবকটা যায়নি বোধহয়।
এই সোহেল, তুই কি যাদবপুরে আছিস? যদি যাদবপুরে থাকে স্যারের কাছ থেকে আজকে নিয়ে আসতে পারবি ভিডিওগুলো শীর্ষ?
না, বাড়িতে রে।
না না ঠিক আছে, যেই হোক সে আমাকে একটু আগে ফোন করে এসো, আমাকে ওটা কালেক্ট করতে হবে, আমার কাছে রেডিলি নেই, আমায় ওটা নিতে হবে, এবং যে আসবে সে একটা পেন ড্রাইভ নিয়ে আসবে যাতে স্পেস আছে, যাতে আমি ওখানে দিয়ে দিতে পারি।
স্যার কত জিবির মতো হবে ওইগুলো?
এটা আমার এক্স্যাক্টলি মনে নেই, যেদিন আসবে আমাকে একটু বলো, আমার মনে হয় একটু একটু বড়ই হবে, ঠিক আছে?
না,
আমি
আমাদের
দেখে বলে
এখানে
দেবো,
কেউ
আমি গ্রুপে
থাকে না
লিখে দেবো,
পাশাপাশি আর কি।
শোনো আমি
আরে
গ্রুপে লিখে দেবো কত কত জিবি বা কত এমবি কি, আমি সেটা গ্রুপে আজকে যাচ্ছি, আমার এক্স্যাক্টলি মনে নেই, আমি জেনে গ্রুপে লিখে দেবো, তাহলে অ্যাকর্ডিংলি ইউ ক্যান কাম প্রিপেয়ার, আর আসার আগে আমাকে ফোন করে আসবে।
ওকে স্যার। স্যার অপশন ওরা যাদবপুরে কাছাকাছি থাকে, তো
না
ওদেরকে
ঠিক আছে, ঠিক আছে, যেদিন যে আসবে আমাকে, আজকে যেমন আমি আজকে পারবো কিনা জানি না, আজকের দিনটা বাদ দাও, যেদিন আসবে সেদিন একটুখানি ফোন করে এসো, আর যদি অন্য গ্রুপের কেউ নিয়ে থাকে অন্য সাবসেকশনে, তাহলে সেখান থেকে একটু কালেক্ট করে নাও।
হ্যাঁ, ভিডিও তো সবার একই হবে, মানে অন্য
একই
সেকশন
একই
থেকে।
একই
হ্যাঁ, একই,
একই
তাহলে
video,
ঠিকই আছে।
ওকে স্যার,
সবার
ওকে
একই video।
ওকে স্যার।
এই তাহলে সৌম্যদীপ, সায়ন্তন এদের বললে হয় না?
একবার
ঠিক আছে,
জিজ্ঞেস
একটু
করি
দেখে
দেখ।
নাও, একটু দেখে নাও, আমি অফ করছি, হ্যাঁ।
ওকে স্যার, থ্যাংক ইউ স্যার।
থ্যাংক ইউ স্যার।